Welcome to the third video of Module 3 on exponential equations. We want to recall the more general version of our exponential equation where y is equal to a times b to the power of x. A is your initial value. It's also your y-intercept, so the value of y when x is equal to 0. B is the base, or the common ratio, between terms. In the last video, where we had a table of values of an exponential relationship, we were able to see that from subsequent values of y, we examined the common ratio between each of those values. The focus of this video will be to examine several application problems which involve exponential equations. Our first example is of an exponential growth application. It says the number of bacteria present in a culture N at time t in hours is given by the following equation. N is equal to 3,000 times 2 to the power of t. Part A asks, what is the initial population? If we recall from our general form of an exponential equation, our A value represents the initial value, and A is equal to 3,000. Therefore, the number of bacteria initially present are 3,000. In Part B, we are asked how many bacteria are present in 24 hours. What that means is that we're asked to calculate the value of n when t is equal to 24. So when we sub in the value of t is equal to 24, we get the following equation. We are asked to express our final answer in scientific notation rounded to 4 significant figures. It is likely that your calculator would already represent this number in scientific notation, and then we look at the coefficient to round it to 4 significant figures. It is found that there are 5.033 times 10 to the power of 10 bacteria present after 24 hours. Part C says to complete the table of values for the equations and sketch the curve below. Pause the video and fill out the table of values. Recall n is equal to 3,000 times 2 to the power of t, and to calculate each value of n, we substitute the value of t into the original equation. Now that we have a table of values, we can plot each of the points on the given curve. Because the horizontal axis represents time, we will start time at 0 and increase to the right because we can't have negative time. Label each of your axes based on the given application problem. On the horizontal axis, we're representing time, and make sure you show the units for time, so in this case it's hours, and then we have the number of bacteria in thousands shown on the vertical axis, and we'll go up by, I guess, every 3 units we will show 200,000 bacteria, so 200, 600, and so on. Rather 400, 600, 800, so we can represent all the values of n from 0 up to t. We know initially at time 0 we have 3,000 bacteria, so it's almost looks like it's at 0 on this graph. We need to mark the values of time on the horizontal axis in order to graph the rest of the points. And we can see here that after 2 hours, we have 12,000 bacteria. After 4 hours, we have 48,000. 6 hours, we have just shy of 200,000, so 192,000. And after 8 hours, we have 768. Now we want to connect each of the points on our graph using a nice, smooth, continuous curve. And we can see that we've graphed the equation n is equal to 3,000 times 2 to the power of t. And we should label our graph. The whole chart can have a title such as bacteria growth versus time. And here's a finished graph of this equation. Okay, well done. This is a lot more work to graph something like this by hand. Recall everything we looked at scatter plots. With linear equations, you could also graph this in Excel and make a nice tidy graph with an equation as well as labeled axes and a title. This is a pause and practice moment, so pause your video, give this question a try. It's very similar to the last one, and you can come back and compare your solutions to the remaining part of the video. So it says, according to the projections by the Alzheimer's Association, the total number of people in the United States with Alzheimer's disease in millions is approximated by n is equal to n naught, so n with a subscript of 0, times 1.023 to the power of t, where n naught has been calculated to be 4.23 and t equals 0 corresponds to the year 2000. So this tells us that in the year 2000, we initially have 4.23 million people with Alzheimer's disease. So pause and answer the following questions. Part A says the general equation, exponential equation, is of the form y is equal to a times b to the x. For the equation above, what is a and what is b? First thing we should do is substitute our value of n naught into the original equation. We know that n is equal to 4.23 times 1.023 to the power of t. Therefore, a is equal to 4.23 and b is equal to 1.023. Next, we want to predict how many people in the United States had Alzheimer's disease in 2016. Remember that since t equals 0 corresponds to the year 2000, that means that the year 2016 refers to the value of t is equal to 16. We want to calculate the value of n for t is equal to 16. So we calculate 4.23 times 1.023 to the power of 16. This is equal to 6.08623 ... and so on, which we would round to 3 significant figures at 6.09, since the initial number of people with Alzheimer's disease in the United States is 4.23, which is reported to 3 significant figures. Therefore, relating this to the original problem, approximately 6.09 million people in the United States had Alzheimer's disease in 2016. Okay, well done. We've taken a look at one of the possible numbers of people with Alzheimer's disease in the year 2016. Now we want to look at making a prediction of how many people will have the disease in the year 2050. So for this, we use the value of t is equal to 50 and repeat the same process that we did for part B. We calculate the value of n for t equals 50 and round to 3 significant figures, we get 13.2. Therefore, in the year 2050, it is estimated that 13.2 million people in the United States will have Alzheimer's disease. Part D asks, by what % is the population growing each year? To investigate this concept, we're going to refer back to our original equation for an exponential equation. If we look at y is equal to 4.23 times 1 to the power of x, we see here that our b value is equal to 1. You can plug in any value of x that you like, and you will see that our value of y will always be equal. So when b is equal to 1, there is no growth. Whereas when b is equal to 2, there's doubling at each time step. So 4.23 times 2 to the power of x, we plug in 0, then we're going to get 4.23. When x is equal to 1, our population doubles. X is equal to 2, you're going to double the amount that was there at the previous time step, and so on. And so you'll see 100% growth or change from one x value to the next. So when b is equal to 1, there is no growth, therefore 0% growth. When b is equal to 2, we saw 100% growth, and we can actually generalize the behavior of the growth rate by expressing the following formula. We can express the growth rate as a percentage as b minus 1 times 100%. Specifically for this example, we get 1.023 minus 1 times 100, which can be expressed as 2.3% growth. Therefore, each year the population is growing by 2.3%. Okay, well done. We just finished 2 application problems of exponential growth. In the next video, we'll look at applications of exponential decay.